What is self-excitation? In fact, we have examined a little bit here in the shunt connection. We said, first of all, there must be some residual flux in the machine. Such a flux will induce some residual EMF. Beep beep. It was here, ladies and gentlemen, ER. Now, we were talking about self-excitation. First of all, in the poles, you just observe residual flux. When you rotate armature at the speed of rated speed, and then here you see, let me change color. Here you induce ER, that is field current versus EMF, and Houston, it is ER here, even if there is no field current yet. And then it will be like this. Before self-excitation, you need to have residual flux. First rule, there must be a residual or remainance flux on poles. I mean phi must be different than 0. And then you rotate. You should rotate machine. But after rotation, electromotive force will be induced, you know. Here is the residual flux. Here is rated speed. After you have rotated the system, here is residual flux, EMF in the system. That residual flux in the shunt machine, self-excitation of shunt DC generator. Here is the electromotive force, dynamo. Inside the dynamo we have induced remainance or residual EMF. That EMF will supply field current of system. That is the shunt generator. And after having ER over R shunt, let's say shunt field coil, R shunt, here is field current, Houston, field current must add to phi R. What I mean, in the poles here were residual flux, and then you have induced some electromotive force. It caused some field current. That field current will generate some field, and it must contribute the first one. What I mean, for example, if you rotate the system in reverse direction, electromotive force will be negative, field current will be negative, so the field produced by field current will reduce the total field. Total field will be reduced due to reversing field current. So rotation direction and field coil connection must be correct. Correct means having cumulative increasing flux. For example, if you switch those two, instead of connecting here, connect C here, D here, for example, it is reversed, so field current is reversed. When field current is reversed, produced field is reversed, so cumulative magnetic field in the pole will be reduced due to wrong connection. If you make a reverse rotation, it will cause again losing phi. If you leave such an event, if you leave this, that cause losing phi. Phi will be lost due to reversing magnetic field. You have eliminated phi. So to have phi, initially shunt coil must be excited by an external power supply. Okay, first of all, you have a brand new shunt generator. There is no current yet. You are on a mountain. You want to induce electric power, so you need an external power to make initial excitation. You connect these shunt coil to an external power supply, and then there is a field current, and then that field current will produce a residual flux, zeroth condition. There is a residual flux right now, which is phi. And then we rotate the machine in correct direction, and then we have induced electromotive force. The second one, ladies and gentlemen, take care. I want to take this equation down to here. Field current is equal to ER over total resistance of the loop, in the loop. Total resistance in this loop right now. And in the beginning, the induced EMF is ER. Now, ladies and gentlemen, take care. What are the components inside these total resistance? There is shunt field resistance. There is a field controller rheostat of generator, that is rheostat adjustable. And there is armature resistance. There will be some startup or starter rheostat. Again, this guy is adjustable. Now, ladies and gentlemen, assume that I have added here a 100k ohm resistance. Here would be quite tiny field current, and that field current perhaps will make no contribution here. Okay, in fact, it can looks like accumulate, but assume that here is 1 megohm. Let's say 1 megohm, 10 to the 6 ohms. And here would be microamps or picoamps. So self-excitation process cannot be maintained in such a high resistance case. What you mean? I mean, let me explain you. EMF, let's say EMF in general, EMF, not ER. It is correct if I say in no load case, it is correct. EMF is equal to IF times total resistance. Here you see total resistance. That must be correct. Okay, that must be correct, and that must be satisfied, correct, and satisfy the operation. What do you mean? Remember no load curve. Here's a Cartesian system. Here's field current. Here's EMF. The relation looks like this. That is the average magnetization curve. That's no load curve. We have already studied in the previous session. Here you see. That was the initial test. And then after conducting initial test, the later tests will be like this. From here, somewhere here, the steady state operation will be like this. That is average magnetization curve or no load curve. Houston, it starts from ER due to residual flux, and then it saturates due to overexcitation. Okay, and now Mustafa means that here's a dynamo, drives a load. Let's say here would be a load, and the load needs a certain terminal voltage, let's say 110 volts, for example. And here would be some resistances, okay, controllers, okay. And here is the excitation coil, shunt coil, okay. And then here's field current. Here would be in the future load current. So, what I mean, what Mustafa means, inside the system there is EMF, and here is terminal voltage. And here is such a Kirchhoff's voltage law. When there is at reasonable, let's say 110 volt output voltage, here must be a reasonable voltage. I got it. Because we induce electromotive force here, and then we deliver electric power and voltage up to here. That is the point where we induce electromotive force. That's the place, which is armature. And then there must be a reasonable voltage because we drive some electrical load here. What is the reasonable voltage? Reasonable voltage will be, for example, somewhere here, somewhere perhaps here, but not here. Not here. Those are very small amount of voltages. For example, you've got Ferrari, you drive Ferrari at the speed of 40 or 50 kilometers per hour. If you have Ferrari, sometime you should drive it at the speed of 200 kilometers per hour, for example. The reasonable voltages would be here because you pay money for the flux, you pay cost for the flux density. Flux density is equal to flux over cross-section area. To have such a reasonable flux density, you have increased cross-section area of the magnetic core, and it gets weight, it gets costs. So you spent much more money for the Ferrari, so you should drive it. Ladies and gentlemen, there must be a reasonable induced EMF. That is the solution region. Solution is being on this curve. I mean, product of these terms must be on this thick curve. Yes, field current times blah blah total resistance must be on this reasonable EMF. Remember, one port systems. Here is a simple one port system. having only one port. I don't know what is inside the system, but we know that we apply some voltage across the terminals, let's say 1 and 2, and here would be some current. And what is the terminal law? Terminal law of the box A. Terminal law for the box A. Let me imagine there is such a relation between voltage and current. There's a straight line. Okay. Here you see voltage over current makes resistance. The slope of the curve, which is constant here in this example, and it is a kind of resistance. It looks like Ohm's law. Tata, the device inside the box A, there's Ohm's law. Ohm's law is working inside this box. Yes, I just imagine the box looks like this. In fact, there will be some nonlinear loads. But here in this case, it is linear. Okay, I assure you. Here's a nonlinear linear relation, and you understand that the tangent, the derivative, the slope is resistance. Houston, it looks like a terminal law. Here, take care. We know circuit theory. It looks like a terminal law. Voltage versus current. It looks like a terminal law relation. So, the slope of the curve defines a resistance. Let's say R critical. R critical. Critical means, I said, for the reasonable voltage, that is the solution. You must be on this line. Okay, let's say R critical, and let me make a final conclusion. This point is important. Total resistance in the loop must be less than R critical. Houston, total resistance, you know, it is RA, R startup resistor, adjustable, R shunt field, R field controller of generator, blah, blah. Any added resistances in the loop that construct total resistance. Summation of all those resistances must be smaller than critical resistance, which is coming from no load curve. And let's say here is total resistance 1. You have added some extra resistances here, and you have total resistance 1. In such a case, possible operating voltage will be this. If you make it smaller, for example, let's change these external rheostats to a smaller value, so you can have total resistance 2, which is less than the previous one. And the possible solution of EMF induced will be this. Houston. And then, if you decrease resistances around this loop, total resistance will be like this. Let's say total resistance of 3, and it is again less than the second one. That is the possible operating point. Here you see. And it looks good. Third value of the possible operating point. Houston, tell the exact story. I'm telling the exact story. Houston, first of all, there was residual flux. Residual flux will induce a remanence EMF. Remanence EMF has caused some correct field current, shunt current, let's say shunt. And then that correct field current produce some shunt field, and if there is a correct connection and rotation, that shunt field current, magnetic field lines will contribute to residual flux and gets a cumulative result. Adds more, will increase, for example, Houston, if it increases, remember Ka flux speed makes EMF, there's an increasing EMF. Increase in EMF result in much more shunt field current. It will result in much more shunt field. Such a shunt field will increase total pole field. Again, increased total flux will result in much more EMF. And then that increased EMF cause much more field current. It will introduce some more additional flux, and total flux of the pole will increase. Houston, what is happening? It is in positive feedback. It increases every time. Yes, but the solution is on the curve. When there is this line, total resistance line, crossing the no-load curve, that is the possible operating point. It is defined by here. That is the possible operating point. And the set excitation process I have explained here. That is the self excitation process. Continues up to the cross-section point. If there is a high resistance in the circuit, there is no self-excitation. Voltage will increase up to here. If there is a high resistance again, voltage will continue increasing, Houston, but possible operating point would be here. So it depends the resistance in the loop. Everything on this loop will affect, but here you see, let's increase, let's skip all those resistances, external resistances, for example, and then here would be such a R4 only having R shunt field plus R armature. There is no additional one. In such a case, here you see possible operating voltage is close to the previous one. Because machine is saturated, gentlemen, there is a saturation. There is no more increase in the EMF due to saturation, because here's a curved line. Here's a straight line, but here's a saturation curved line. That was the self-excitation process, and it was very important. In case you are in difficulty to understand this topic, Here is in Turkish version I have uploaded onto YouTube. Please watch this. It is 33 minutes, you see. Please watch Turkish version if you are in difficulty.